Hi guys, hope all of us are doing great. My name is Ernest and this is Ernest Sciences and Mathematics TV channel. So today I'm going to look at a set of problem, and this is going to be of course a follow-up discussion from the first video we are done on electronic spectrum. And of course we're going to see that this is going to be an application question where we are going to be required to find the energy required to remove an electron from the second energy level of Bohr's orbit. So in this particular case, of course, we will also be required to find a wavelength of this specific radiation that is being involved in this particular transition. So in order for us to tackle this specific question, I'm going to look at a set of course, ideas, all that discussion that we had done, especially on the concept of energy. And I'd mentioned, of course, in this specific transition in an atom, we're going to consider the case of the energy that was discussed from the Planck's quantum theory, whereby we said that Planck basically described the energy that is going to be involved in this particular emission as of course, the product of frequency, and of course, it's going to be related to the frequency with this specific constant for Planck's constant given as h. And as we said, this is going to be a constant which is going to be given in a particular value of 6.62 times 10 raised to negative 34 joule seconds. And of course, we said that this is going to be in collaboration with Einstein's energy mass description, which are going to give us an overall view of the aspects of quantum mechanics. And of course, for us to just find a way of describing this specific energy, then therefore we are going to consider the case of the wave particle or duality nature, whereby we said we can be able to give this energy in terms of the speed of light and wavelength given as such, and therefore this is going to form a basis for us in trying to solve our particular problem. So in that discussion, I had mentioned that we can be able to give the energy of an electron in a hydrogen atom, which is going to be given as E subscript n, and this is going to be given as a product of a -1 or negative 21.7 times 10 negative 19 joules. And then this is going to be the ratio between this particular value and n, whereby we said that n is going to represent the level or this particular level of the Bohr's of course orbit given in terms of n. So in our case, if we are required to calculate the energy required to remove an electron completely from the value of n is equivalent to 2 orbit, we're going to apply this specific formula whereby the value of n is going to represent the second orbit, and therefore I do a substitution for this, which is going to give us 10 negative 19 joules, and then all over the value for n is going to be 2, so this is going to give us what we refer to as the square of 2. So from our evaluation, we're going to find this one giving us a value of negative 5.425 times 10 negative 19 joules, and this is going to be the energy that is going to be involved in removing this specific electron from the second orbit. Now in this particular case, then therefore we will also be required to find the wavelength that is going to be associated with this particular radiation that is going to cause this particular transition from n is equals to. Then therefore for us to find the specific wavelength, we're going to apply this. Let's assume this is our first equation. We're going to apply equation 2 in order to find that. Now that we have found energy, the speed of light and the Planck's constant are going to be given in terms of course, constants, and therefore we are going to make this specific a set of equation using, or rather this specific equation by using lambda as the subject of the formula, and have it as ch change in h over that one. So if we do a substitution, then therefore we're going to have it given as 6.626 times 10 negative 34, and these are going to be in terms of joules, and this is going to give us with the product of 3 times 10 raised to power 8 meters per second, which is the speed of light. divided by the change in energy that is associated with this specific transition. So this is going to give us 5 for 25 times 10 negative 19 joules given as such. So this is going to give us a product of 3.664 times 10 negative 7 meters as the wavelength of the radiation that is going to be causing this specific transition. So of essence for us is to remember the basic rules which of course we are used in evaluating the energy of a photon, and of course the Planck-Einstein's energy mass relationship, which is heavily going to be applied under various topics in quantum mechanics. And of course for us to remember also is this particular formula, which is generally used to give the transitions, energy transitions between various Bohr orbitals given as such. So catch us in our next videos. We're going to look at the other aspect of the energy transitions, and perhaps some of the transitions that we have mentioned for the Palmer, Bastian, Pfand, and Lyman series respectively. So that is it for now, guys. Bye, God bless.